Hey everyone, let's continue on a presentation of evolution. So now we'll talk about Hardy-Weinberg, and we'll talk about the difference due to that really unnatural situation that Hardy-Weinberg is setting. So as a reminder, we were talking about evolution. You have three conditions for evolution by natural selection: variation of a trait, heritability of a trait, and differential reproductive success, right? So how do we know when it happens? Meaning, how do we know allele frequencies are changing? What we do is we set up a absolutely hypothetical population in which Hardy-Weinberg takes place. And for that, we have those assumptions. No natural selection, no mutation, the population is large enough to eliminate random changes in allele frequencies, individuals mate at random, and there is no migration. So immigration, nothing comes in and out. You don't choose your mate on any characteristic, you just mate at random. There is no natural selection, so there's something is missing, either variability of a trait, heritability of a trait, or differential reproductive success, right? All of those, when those are met, then you get those two equations. Those are huge. Why not? What you have here is one of them explains the allele frequencies. So this one here is allele frequencies. Whereas this one here shows the genotype. I should say alleles and genotypes, frequencies. Writing with a mouse here. I should maybe use my iPad for that, but you know, it works. How do we know those are frequencies? The way we know that is they add to 1. So a frequency is kind of like a percentage. How much of a population has the dominant allele and how much has the non-dominant allele, the recessive, right? And they must add to 1 because the situation has only 2 alleles, one dominant, one recessive. So we're not talking about codominance, incomplete dominance. We're not talking about genetic drift. We're talking about normal, like not normal, but like regular old school dominant inheritance. Those are allele frequencies. When you look at what these do in genotypic frequencies, you have to realize you already know where that's coming from. So how do you know? Well, when you look at your simple delimitation, if you look at the gametes, right? You have a male and the female gametes here, and imagine you have a situation when you have the dominant allele being D and the recessive allele being little d, then the male gametes are the same. The reason why we go for heterozygous, this here indicates that your parental individual was big D, little d, in parentheses. And same thing here, big D, little d in parentheses, which is why you have half of the gametes being big D and half of the gametes being little d, right? Now we want to remember that big D equal P and little d equal Q, right? When you do this, you realize that when you draw your Punnett square, what you get is a shorthand version, and let's draw it together. That will be easier. Let's draw it together, and I'm going to use coloration. So let's see. We're going to use the dominant allele would be red, right? So I'm going to convert the numbers, the letters. Big D from here, I put it here. Then I put a big D here. Big D here, I put it there, and then here I put it on the first position because it's a dominant allele. Right, and what we'll do is we'll use green for the recessive allele. So little d is here. I put little d there. Little d first, right? Then little d here. I put it there, and I put it there, right? And that's basically your Punnett square. right? Everybody gets that? So when you look at this, you have genotypes of of offspring from both parents, and if you have to look at the ratio of phenotypes, you will have one that would be green, and you will have three of them that would be red, correct? So it's a 3-to-1 red to green, and in that case it's dark fur and light fur. It's ferrets. So once you have that understanding, that's that 3-to-1 ratio here, explain the phenotypes. And if we want to actually make it extremely clear here, let's do this. A phenotype is written in brackets with the allele that is expressed for said phenotypes. So it's a 3-to-1, and those are the phenotypes. Now if you look at the genotypes, those are phenotypes and I will say phenotypic ratios here. And if I'm looking at genotypic ratios, or just ratio, what I have is homozygous dominant D, and I will put it in parentheses. You have one of them, and then you have heterozygous, big D, little d, those you have two of them, and then you have homozygous recessive, and you have one of them, right? 1-to-1. So those are the genotypic ratios. Now, if you want to write this in math, you can write this P, the dominant alleles, plus 2P. Actually, let me plus P Q2 plus Q equal, and the sum of all the genotypic ratio, which are all the offspring, must be 1, because those are genotypic ratios, so they're going to all add up to 1, right? And if you want to even simplify that, you realize that this is here p square plus 2pq plus q square equal 1. And you see it in the diagram. You have 2pq here, you have p square here, and you have q square there, right? So you can see the typical ratio, and that's the equation that's up there. P square plus 2pq plus q square. That should be a plus. There's a mistake in the diagram, in the PowerPoint. Okay, anyway. Oh. It's fixed later on in the PowerPoint. So now that we understand where those equations come from, we realize we don't need to learn the equations by heart, we can just understand them, right? So now that we understand them, let's take a look at what it means. If you look at the population of ferrets, because we've been working with a ferret's equation here, when you look at that population, you see individuals, and you cannot tell for the dark fur individual, the one expressing the dominant phenotype, the homozygous dominant from heterozygous. You cannot tell them apart. They are literally identical from your point of view. They look with dark fur. However, the recessive genotype, the p square, the q square down there, that is the one that matches genotype and phenotype. The phenotype is recessive, the genotype is homozygous recessive. Thus, by counting those, you can find the frequency of those individuals. So in this example that we have here on the board, we have 1, 2, 3, 4 little d, right? We have 4 individuals that are homozygous recessive. Now if that is divided by the total number of individuals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. This is going to be the frequency of homozygous recessive QQ divided by all individual. So that's why it's a frequency. And that means this is the Q square. Because that's the genotype, that's the number of individuals that have that genotype divided by all genotypes. That's Q square. So you can find Q square by just counting the number of recessive individual phenotypically, you know genotypically they match. So you know you're looking at Q square when you divide by the total population. When you have Q square, you can be square root of Q square equal Q. Once you have Q, you can be 1 minus Q equal P. This comes from that equation up there. P plus Q equal 1, so you say P plus Q minus Q equal 1 minus Q. Simplify for those two here, and it's P equal 1 minus Q. I just solve that equation for P instead of equal to 1. And now that you have P, you can just find P square. And now that you have P, you can find 2PQ. Right? So by looking at the recessive phenotype, we can find all of our answers that we need, right? So at the exam or anywhere that I give you a question and I give you the percentages of a number of whatever, you should be able to work your way through those equations. So I can give you different stuff, right? I can give you the frequency of the dominant allele in this population is 0.6. Now you can find out Q because it's 0.4, P plus Q equal 1. And you have to look at what the question is asking. So if I tell you the frequency of a dominant allele is 0.6 in this population, what is the frequency of heterozygous individuals? You do 0.6 minus 1 minus 0.6, 0.4, that's Q, and so now you have P and Q, and it's 2PQ that you're looking for. So it's 2 times 0.6, 1.2 times 0.4, and that would be 1.2 times 4, which is 4.8 divided by 10, which is 0.48, I believe. Is 0.6 times 2 times 0.4, 0.48. Here you go. Because you can multiply by 4 instead of by 0.4, but then you have to divide by 10, that's all. That's how I did that. So here you go. You can answer those exam questions now. So make sure you're working your way through this and understanding how all those equations work. There is a lab that's on this, so you can cover it via the lab. And then the main point of Hardy-Weinberg, the way we set up that situation, is to be able to detect deviation from Hardy-Weinberg. It's a moot situation. It doesn't exist in nature. There is always immigration, emigration, death, birth. There is always non-random matings, all of that, right? Because the probability that some ferrets mate with others is probably higher with the one closest to them than the one away from them, right? And that's not accounted. In Hardy-Weinberg, it says, nope, they can mate with the one on the other side of the savanna and the one next to them equally, which is not true, right? But when you look at the reality of what's happening in the population and you look at the difference between that and Hardy-Weinberg, you can tell what is happening. And we don't learn that in BIO112, but we have statistical way to analyze the differences, the discrepancies statistically between Hardy-Weinberg and what's observed to detect what type of evolution is happening. Is it just migration? Is it genetic drift? Is it a mutation? Is it evolution by natural selection, sexual selection? They all leave different traces into the allele frequency changes. And with that, I will leave you to it. And yeah, I'll see you in the next video. Bye.